background on Paulo. He's a CTO of Empower RF Systems with decades of experience in RF engineering, wireless communication, and broadcast networks, hardware and software. Today, Paulo will share with us how the advances in solid-state technology is moving the industry forward. And with that, the floor is yours. I made the TV take a nap too.
Here we go. Okay, thanks for having me here today. Good afternoon for everybody. My name is Paulo. I have been in the industry, RF and microwave industry since 1975. So it's quite a long time. And mostly in broadcast. Initially I worked a lot in broadcast with tubes. At that time there was tubes and that's it. The maximum power we could get on a device was 5 watts. All right, so the RF and microwave have moved a lot since then. Okay, and it's not easy to keep up with everything that's going on. And lately, because the process of semiconductor has been extremely improved, okay, we can get new materials like gallium nitride and very high power devices. Okay, I'm working with a manufacturer that's going to get us a device with 600 watts CW capability at 1 gigahertz, broadband device. So even the ratio between power and size and frequencies being changed completely in this industry with the evolution of the device technology. Okay, pretty much like in microcomputers, microprocessor, the RF is also evolving. Okay, and we have been trying to do that with our equipment. Okay, so basically, we're going to go with an introduction what is Paulo, what we do. Okay, a quick look on our architecture, what we have done. Okay, which is the multi-mode and interoperable power amplifier, which is very, very important. How you set that, okay, how you set the amplifier for multiple missions, okay? And we're going to talk a little bit about frequency hopping and blanking, which is a very complicated situation. Frequency hopping is fast, the blanking is slow, and keep up the automatic level control to keep the power constant, even when you're hopping and blanking at the same time. It's like walking slow and walking fast at the same time. Okay, we're going to also talk about pulse shaping, which is power amplifiers distort pulses, okay, and how you do it to make the pulse exactly equal to the input pulse. We're going to talk about that kind of technology. And in the end, which is not here in the agenda, I'm going to talk a little bit about scalable power, okay? How can you go from, I buy a 5 kilowatts amplifier, and I don't need to buy another one to have a 10 kilowatts. I can upgrade the 5 kilowatts and step up the power. Okay, and how you do that, for example, in very, very high power amplifiers, how you do that being hot swappable. You can take the whole box out of the chassis with the amplifier work and plug another one in. Okay, with full functional amplifier. Okay, so that's what we're going to cover. If you guys have any questions, I don't know what you prefer. If you want to ask the question during the presentation or at the end, doesn't matter to me. If you want to interrupt and say, hey, please explain more of this, it's okay for me. Okay? So first of all, what's Empower? Empower design, manufacture, and sells power amplifiers from a little box, a little building block with 10 watts, okay, to 10, 25 watts to multi-kilowatts amplifiers. Okay, what's unique about the amplifiers that we transitioned. Paulo was born in 1999 with an entrepreneur that built the company. Okay, with the IEDs in Iraq, this company did a lot of work with the electronic warfare to jam the IEDs. And it was used, and that gave a ramp up because it was thousands and thousands of amplifiers to be deployed in the field. The company was then bought by an investment company that still today owns the company since 2006. And when they bought, they decided to build a staff, a management staff that was professional, not family, friends, and okay, so that's where I came in and I started working in the company. All right, so initially amplifiers were done. Okay, they have a potentiometer or a control, a gain, a frequency and a power, and that's what it was. When I came to the company, I come from doing amplifiers for broadcast. Broadcast is not like this. Okay, the amplifiers are intelligent. Okay, I did intelligent amplifiers in 1994, 95, for broadcast with a microcontroller, all the bias being automatically done by software. No need, no adjustment whatsoever in the amplifier. Everything was electronically controlled. And when I starting in power, I had the impression that I'm going back to the Middle Ages, okay? Way back to the past, because all amplifiers were potentiometer, everything has a trim pot, a trimmer, a cap, a variable cap, etc. Forget all that, let's start from scratch. And that's what we start doing, intelligent amplifiers. I brought to that industries also the idea of using a browser to control the amplifier. So you just open up your Firefox or your Chrome, you connect to the amplifier and you can see down to the last device, the last transition. You can see everything inside it. And this is because a browser, everybody knows how to use a browser. Okay, so it's very, very simple to do. Then you have to understand that doing a specific amplifier for each one of the markets would be very complicated. Okay, and too much of one. So what we decided to do is, what are our markets? Our markets are radar, communication, electronic warfare, which is basically jamming power into the bad guys, and test and management. So what we decided to do is do a multi-domain amplifier, where by software you query the amplifier and transform it on what you want. Okay, so you can go from CW to digital modulation, OFDM for 5G on the same amplifier. You just have to tell the amplifier what you want it to do. That's why it's a multi-domain, okay? And it's interoperable because you can move from one application to the other application without having to change anything in the PA. Okay, so to do that, we had to do a lot of stuff different from the way that normal power amplifiers do. Okay, so we had to, for example, detection. We have both detection. we have peak detection and RMS detection. You go to digital modulation, it jumps direct to RMS detection. You go to AM modulation, jumps direct to peak detection. Okay, so it uses the detection mode that's appropriated to the application that you are using. And that's why, because we can buy today devices that measures RMS through RMS and give me the envelope. Once I have the envelope, I have the peak. And so the evolution of the semiconductor allow us to do in the amplifier way more finesse or nuances so that the amplifier can be used in multiple ways. The other thing is, with digital signal processing, I can see because I have the envelope detection in the input and the output of the amplifier, I can see the difference between one and the other. I can see what's the error caused by the amplifier to the pulse that I know what it is in input of the amplifier. And with this, I can correct the pulse, correct the error, and transmit a high fidelity pulse at the output. Okay, so the intelligence of the amplifier makes it much more open to any application than just the dumb amplifier that you have the potentiometer, and many people still do that, okay, in the front panel. The other thing that we did, and for me is very important, and was almost a little fight in the company to accept that, is what interface to use. Okay, GPIB I forgot in 1990. We stopped using GPIB in the broadcast in 1990 something. Okay, visual basic or the other methods of preparing graphic user interface we didn't use anymore in the broadcast since the late 90s. We started to use browsers in the late 90s. And it was very difficult because, imagine, this industry was very behind on this technology. So it was difficult to convince that you have to move on. Forget GPIB, put Ethernet. So all our amplifiers is Ethernet connection. 100 megabits or 1 gigabit per second, you just put your cat cable there and you have access to the amplifier. Now, somebody can say, no, but I want GPIB. I can put a dongle there and transform a serial port to a GPIB, but it's slow, it's not very efficient. And besides GPIB, the components are not evolving anymore. Nobody in the industry is investing in chips and components for GPIB. So we can use it, but I think that Ethernet is much more appropriate. Okay? So basically, this describes what it is. Okay? Any type of detection, as I said before. Okay? Any type of output management, power management. And what's that? I can use automatic level control, which keeps the output power constant in the frequency range. Okay, so you set the amplifier 1 kilowatt, and whatever frequency you put, it goes to 1 kilowatt. We can do manual gain control, which is what kind of potentiometer, but it's electronically, okay? You set, I want 50% of gain, 70% of gain, and to adjust the gain of the amplifier. You have no automation. It's similar to the dumb amplifier, but electronically controlled. And we have something different. It's the automatic gain control, which keeps the gain constant for the amplifier. What it does is it takes P out minus P in,
output power minus input power, and keep that ratio constant, no matter what frequency you are. Okay, so I can accept any kind of modulation because I have any kind of detection on same amplifier. And it needs to be as efficient as possible in any application. So that was our goal, our design goal, and that's what we have in our amplifier. Interoperable is because I can move from CW to pulse and to digital modulation. No matter what, I can do whatever you want. And why that's important? Because waveforms are changing like crazy. You have all kind of waveform. You have all kind of application, all kind of requirements for power amplifier. You don't want to have one for digital modulation, one for pulse, one for CW. You don't want to have that, okay? Because it increases too much your investment. So that's why it is important. So that's an example, okay, of a graph user interface that's direct on your browser. You see that, you select what mode you want to do, you save, and the amplifier does the system engineering for you. Okay, you can tell, for example, if you want to do digital modulation, it will appear what's your peak to average ratio of your signal. And you can say 8 dB, and will automatically adjust that your maximum power, average power, needs to be 8 dB below the nominal power of the amplifier. And we'll do that all automatically. Okay? And you can select all kind of operation through the graphic user interface or through the machine-to-machine, the computer. Okay, you send an MSC command, it will set power, set modulation, set everything at the same time. What kind of detection, if you're going to use manual control or ALC, okay? So you can do everything in one string, one simple command. Or you can use the graphic user interface in the front and in the remote, in the computer. That's a laptop, okay? It has the same GUI on the display, local display on the amplifier. Okay, of course, it's condensed to a small screen, okay? This one is large screen, the other one is condensed to a 4.3 inches screen. But you have access to it. Okay, and you can set 7 presets. You have 7 configurations that you can set. Give a name to that configuration, and you just recall it, and we will automatically go through that configuration. It's like what you do in an instrument, and you recall the setting, and it comes back. Any questions? So let me see if I can do this. But the idea here is to show you the fast, this low, and the power will be kept constant, no matter what I'm doing with the frequency. Okay, the frequency changes in 10 microseconds from one to the other, and the blanking is turning on and off the carrier at the same time at about 10 hertz. And you're gonna see that the power is kept constant, no matter what. I don't know why it's not playing? It should play.
Space bar. Hit the space bar. Yeah. That didn't work.
Don't know why. Let me see.
Where do you have another file of that folder? OneDrive?
Everything was together. It was inside the folder, inside the slide.
Oh, well.
Probably can exit the presentation mode.
I'm sorry?
Exit the presentation mode.
Good escape.
Get out of presentation.
Yeah.
Probably just, yeah, on the file. With the media player or something.
Everything's played now. Right there.
If this. Oh. I don't know why. It's not gonna find. Okay. Sorry. But believe me, the power is gonna keep constant. You're gonna see the frequency jumping around here, and the power here constant, and the pulse all together. I don't know why it's not playing.
No worries.
Okay, now let's talk about the pulse shaping. Pulse shaping is very important, for example, for a case of radar, countermeasure radar. Imagine the following: the guy send a pulse to detect an airplane. Okay, if the airplane sends back same pulse with the same precision on the transitions of the pulse, okay, the radar is gonna think that you are in the wrong place and cannot track you. Okay? So that's one of the technology that's being applied because the stealth airplanes don't work anymore in certain conditions. They can use low frequency radar and it's gonna detect because the painting and the material that's used to absorb the waves cannot absorb HF radar. Okay, so if you send it back the pulse with fidelity so that the radar guys cannot see that's coming from another equipment, that's not the reflection of the pulse into the airplane, then it will think that you are in a different position. Okay, that's why the pulse shape is very important because you have to send back exactly the same pulse that's hitting you with all the errors and misinformation that is generated by the propagation and the reflection. Okay, you need to send it back. All right, so that's why the pulse shape is important. And to reduce the distortion of the PA. PAs will distort the pulse no matter what. You will have droop, you will have a ring, and if you use TWT, it's horrible because you can't correct it. Okay, TWT has ring, and we'll never be able to correct it. The solid state can. So what we basically use is a simple mathematical function.